Afternoon.
Good afternoon.
All right, so we were on chapter 3 with the extended surfaces. So we talked about, the combined conduction-convection, what it is to be a fin, the kind of little bit of how the temperature changes, profile, some fin configurations, the importance of it. And then we got to this point with the fin equation, right? So we're going to develop this equation, and then again go even to that one where we substitute in some kind of factors or constants in there. But how is this derived? And so let's do that. All right, so we're going to start off with, we're going to look at basically it's going to look like this, where we have a fin, and we're going to kind of look at a little section right here. So this is some section dx, okay? So if we do that, all right, so let's write that. So then we do that, all right, so then we have this section. It's got a thickness of dx, right? This area right here is the cross-sectional area. All right, so where do we think, with a shocking question of where do you think we'll start to get the fin equation? What equation would we start with?
Heat equation.
Even before that, heat equation deals with just a pure conduction, okay? But what did we use to get there, right?
COE?
Yeah, just a COE, okay? So because now we have conduction and convection combined at the same time. So we got to go back to the COE. So in the COE, here we have energy in, out, generated, change in energy stored, right? So we need to kind of label our little sliver here. What heat transfers are occurring on this little section of this fin? We need to label what heat is going in or what heat is going out, leaving this. So we said it's combined conduction and convection, right? So I'll do the conduction. We'll have Qx on the left and Qx plus dx on the right. Where's the convection then?
Going vertically?
Yeah, so on that outside surface. All right, so now what can we cancel in our equation? Doesn't look like we've labeled anything with generation, right? Which I think someone was about to say. Cut them off before they could answer. And then the other is we're going to just be looking at steady state. Okay. So then from these components, in is QX, and I'll put QX Swiss dx is out, and then convection is out. That's all equal to 0, right? So we have QX, and then if we do our Taylor expansion like we did for the heat equation, for QX plus DX, we get this. We try it, and same thing we did then, we get to cancel that QX off. All right, so we have this. What do we put in for Q convection?
H times the change in temperature.
Yeah, so we have our Newton's law of cooling we'll put in for that, right? Okay. What do we put in for, so we're going to substitute in for Q convection, Newton's law of cooling. What about for QX? What do we put in for there?
Fourier's law.
Yeah. All right, so we have Fourier's law substituted in there for QX, and it's Q, it's not Q double prime, so we have to have the area there. And then Newton's law of cooling, again, we have to have the area, but what's the area for convection?
Surface area.
It's the surface area, so it's the outside surface, right? So that would end up being the perimeter times dx. So that would end up being, green. This, right, this area. It's P times dx. And then we have the temperature minus T infinity equal to 0. Okay. Now what? Anything we can cancel?
Because we have constant properties, we can bring the K and the area outside, and plus it's one dimensional.
Yeah. And there's also, so we have this that we can pull out, which comes with constant properties. This pulling out comes with uniform cross-sectional area. If we had, instead, it was more like a prism shape, then that cross-sectional area would be changing with X, right? That AC would be changing as you're moving along X direction from X equals, X, where this is X equals 0 right here, and this is at some length L. So it would be changing, so you would have to leave that A cross-sectional in there and have kind of how does that cross-sectional area change as a function of x, and leave that in there, right? So that makes it a little bit more challenging when we have that. So, but we'll, for this derivation purposes, assume uniform cross-sectional area. So that'll pull that one out, okay? And then there's one cancellation. We have dx right here. So then we get KAC. So here we can see the left term tells about, conduction going through, and the right term convection, right? So now we just kind of move it around to help with simplifying and solving. All right, so we have this, and we have two simplifications here. We use m squared is HP over KAC, right? So that means m will be the square root of HP over KAC. They pick m squared because in the solution to this OD is m, so that's why they have the m squared for it. So that's why they did that. And then the other simplification is theta is t minus t infinity, okay? So that makes that non-dimensional too. So with those substitutions, we have this equation, right? The neat thing about theta is if you take theta and you take d theta dx, it's the same as dt dx because this temperature affinity is a constant. So when you take the derivative of that, that becomes zero. So these are the same. So that's the nice part of the substitution, which you'll see a lot in these thermal type heat transfer problems. All right, so now we have something that we can solve that looks more like an equation you may have seen in your math courses. And that's what we have here, okay? So it's a combined conduction-convection solution. So to solve it, we need two boundary conditions, right? We have x squared, right? The second derivative there. So we would have to, have order of two. So that means two boundary conditions, okay? So the first one is going to be right here at x equals 0. We're going to always have temperature of the boundary, and that's this one at x equals 0. The base condition right at this location, okay, is x 0. So that would be the theta base, TV, temperature of the base minus T infinity. So we have theta of the base is known, is our first boundary condition. And then the second one is at the tip, okay? And so at x equals L is our next boundary condition. And it really depends upon what's happening in your application, or whether you can just simplify to maybe one of the conditions that are simpler to get the simpler equation. So we have convection. So if you have convection on the end, that's A. So that's convection on the tip. If it's adiabatic, okay, so the first one would be, you have convection, right? That's A. Adiabatic is if this, is insulated. Fixed temperature is more what we saw right here. This is a fin, temperature 2 and temperature 1, where this could be the temperature of the base that we know, and this is the temperature at the end of the fin at the tip. Okay, that's that one. And then infinitely long fin, okay, is the last case. Okay. All right, so then the two ways of getting the heat rate is basically if we look at, at this surface right here, we do Fourier's law. Right at that surface at x equals 0, we can take the derivative of theta, right, and just multiply times k times AC, and we get the convection that's going through that surface right there. And, or on the other side, if we were to integrate along the whole surface here, so basically along the area of the fin, we just integrate and we get the heat rate. So that would be the heat also on that side, okay? Both of those ways will get you the solution to the fin heat rate. The nice thing about this is there is, the book does go through one of the, ways of getting the solution to a boundary condition or two from this equation that you see here. But then they put all those solutions with those different boundary conditions in a table. So table 3.4, okay? You have your different cases right here. Okay, so the end conditions: convection, adiabatic, prescribed temperature, infinite fin. Okay, and then we have temperature distribution equation and the fin heat transfer equation. So the temperature distribution one is theta over theta b, right? Which is just temperature at some location x minus T infinity, temperature of the base minus T infinity. Okay. So if you want a temperature at some point along the fin, maybe it's at the tip temperature, you want to see how cold or hot it is, then you have that, or maybe it's some location, some mid location, something. So that gives you the temperature profile. And then we have our heat rate. So the amount of heat that's being dissipated by that fin is right here. And we can see, you see better, easier solutions solve, some more difficult. So in this case, you see the convection has a very complicated formula to use. Adiabatic isn't too bad. Prescribed temperature is a little bit more complex to put in. Infinite fin is a very simple equation. Okay, so we have these different forms, and we'll see sometimes of utilizing, say, the adiabatic form instead of convection, just because it's a simpler equation. All right, so then we have performance parameters. Okay, we have the first is the fin efficiency. Okay, and that is your actual heat that's coming off in the numerator. Right, so that's from the equation you see right here. And then the denominator is Q max off of that fin. And really what it's saying is you have convection, you have the area of the fin, okay, and then if it's all along the whole fin was all at the base temperature, okay, so that'd be the max temperature. If at any point along this fin we were always at the base temperature, which it isn't because temperature is dropping, that would be the max heat that you get from it, because that would have the max temperature difference. Okay, so that's your heat max, and then this is the actual heat. So this one goes from 0 to 1. This is fin efficiency. Okay, and they've actually in table 3.5 solved for a lot of these fin efficiencies for these different types of fins. Here you see a triangular fin, okay, and they give you an equation for the fin efficiency. Okay. These last two things, I'll get to it in a second. I'm going to go to the next slide and then I'll come back. So here I show you table 3.5. So here's our triangular fin that I has in the last slide. So that's the example that was given, but we have all these other ones. We have the straight fins, right? And you see it here, fin efficiency. We have you know, an annular fin. We have the pin fin, so just some protruding piece off of it. Okay, and the fin efficiency that goes with it, and what the area of the fin is, the length, and the volume. So nice equations for it. The other thing that they have here is, let me zoom in, is these, you know, they've already simplified for that coefficient m for some of these. So for this parabolic, it's this b1, right? For the triangular, it's b. For the rectangular fin, it is. But then if we go over, say, here, if I can figure out how to use a computer in my old age, we have a. So this one uses the version a, right? Okay. Oh, all right, so the last thing I wanted to show in this table is the L. So if you see here, and I'll zoom, maybe I won't zoom in, I'll just rewrite it. That shows LC is L plus D over 4. And then over here for this straight fin, it shows LC is L plus the thickness divided by 2. So they're adding a length to it, right? So they're adding this D over 4, and they're adding this thickness divided by 2. This is the thickness in this one, and then the diameter, obviously, in that one. And what they're doing that for is they're using the simpler equation of adiabatic fin equation. So they're using adiabatic fin with longer length, and that's to account for convection. So if we look at this, they're using this equation instead of this one, and what they're just doing is adding a little bit of length to L to account for that missed length, that missed heat transfer on the tip. They're just adding a little bit of length to the fin to get some of that that heat transfer back, and it allows them to use this nice simpler equation here versus this one. Okay, and that's what's being done in this table right here, and why they have this, you know, this changed length. They've basically added a length to it to account for convection, but use the simpler equation. So let me go back to this. All right, so we talked about fin efficiency, right? So that was heat off of the fin divided by if the whole fin was always at the base temperature. Okay. Fin effectiveness, its numerator is still heat off of the fin, and it looks similar to fin efficiency, right? Because we have this base temperature, we have the convection coefficient, but the area is something different. This area is now just the base area. So if it was like if the fin wasn't there, if you just had convection along the base area, if the fin wasn't there. Okay, so in this case, though, the fin effectiveness should be greater than 2 for fins. Okay, so with a fin, you should be getting twice as much heat transfer or more. Otherwise, it might be better just to leave it as just the base and not use fins. Okay, it might not be beneficial then. The last thing is a fin resistance. For some problems, it might be easier to just look at a fin as a resistor. Okay, and what it does is you're able to take the base temperature resistor and then T infinity. So, and then this is just basically the resistor for the fin. So they use RTS. Okay, so it already accounts for the convection, conduction combined that's occurring along the fin. So all the temperature change. So all you have to do is look for that one resistor, and that has your heat through it. Okay, so and really, what it does is uses that efficiency. Okay, 1 over H times the area of the fin. So if that fin efficiency was 100%, it would be like the whole fin is at the base temperature, right? But it's not. So you get a fin multiplied times the fin efficiency, and that's where this actual resistance comes from. Okay, so we talked about that. All right, so fin arrays. So what we have just done is for a single fin. So we have just looked at basically just one fin. Okay, now fin array has a number of fins. Okay, so you would have a single fin like that, which has an area to it, and then you multiply it times the number of fins. Okay, but then you also have exposed base that's transferring heat. So like this is the exposed base, this is the exposed base. So that's that. So those two together would give your total area that's occurring for this heat transfer in a fin array. So now we just take that and use that knowledge for a heat rate. Okay, so you have heat coming off of that exposed base, and that's this. Convection, area of that exposed base, and then basically theta is the temperature of the base minus T infinity. Okay, then you have over here the heat off of a single fin. So it's fin efficiency, H, area of the fin, that T base minus T infinity, so that's theta B. And then you just multiply it times the number of fins. Okay. And that gets you your total heat rate. Okay. We can also make an equation where we just have total overall efficiency of the fin array, and then just multiply that times H times total area theta B. And that comes from just looking at these two equations and solving for what the fin efficiency is off of what you see here and rearranging. And that's what you see. They just have basically done that here and solved for the overall efficiency. So this is for the fin array. We can also look at a fin array as just a resistor. So we would just have the temperature of the base, a single resistor, T infinity, and we would have our TO, and that is our, takes into account all the fins, this exposed base, it's just the total overall resistor. Okay, we can just look at that whole that whole fin array is just one single resistor, and it's all in that we have to, the magic that we have to solve. All right, so I already kind of looked at this equivalent thermal circuit. That's that RTO, the overall one, is right here. Okay, it takes in the combined base and each fin, and you just look at it as a single resistor. One last one that I'll show here is if you had, say, surface contact resistance. Instead of, if you took a block of aluminum and machined these slots out of it, right here, right, you wouldn't have any contact resistance between here and here because it's a single piece. But instead, let's say we have something that's huge, a big heat sink. So instead, maybe we're welding those pieces onto the base. So now that weld, or that, however we're connecting it, has a contact resistance. Okay, so that now has a surface contact resistance. We got to take that into account, and that's all this is now that's a resistor overall with contact resistance is a single resistor that now if we go through our equations, we can account for that contact resistance we have there. All right, so then we have examples. So this is 399. All right, so 3.99. Turbine blades mounted to a rotating disc in a gas turbine engine are exposed to a gas stream that is at T infinity 1200 degrees Celsius. It maintains a convection coefficient of 250 watts per meter squared Kelvin. The blades, which are fabricated from Inconel, where thermal conductivity is 20 watts per meters Kelvin, have a length L of 50 millimeters. The blade profile has a uniform cross-sectional area of 6 times 10 to the negative 4th meters squared and a perimeter of 110 millimeters. A proposed blade cooling scheme, which involves routing air through the supporting disc, is able to maintain the base of each blade at a temperature of 300 degrees Celsius. Part A is if the maximum allowable blade temperature is 1050 degrees Celsius and the blade tip may be assumed to be adiabatic. Is the proposed cooling scheme satisfactory? And then B, for the proposed cooling scheme, what is the rate at which heat is transferred from each blade to the coolant? All right, so we see kind of the schematic that was given to us a little bit. With a couple more things kind of plotted on here, but we have our blade, right? They give us this base temperature of 300. They give us the turbine blade, which is this. They have this perimeter given to us. Maybe they went in CAD and grabbed the perimeter and then cross-sectional area. And we have in canal, so we have the thermal conductivity of it. We have our convection that's occurring on the outside of the blade. So basically they have cooling going on down here, and that maintains this blade, right, the base temperature of 300 degrees Celsius. So they said there's a maximum allowable of 1050 degrees Celsius for this Inconel blade, right? So where do we think this maximum temperature then is along this blade?
Can you repeat the question, Professor?
So where do we think this maximum allowable value is along this turbine blade?
Would it be at the base?
Not in this case, because the base is being held at 300 degrees Celsius. So this problem is actually doing a little bit of the opposite of what we normally see. So in this case, where, you know, usually you have the high temperature at the base, and we're trying to get rid of that with the heat sink, right? While in this case, the cooling air is the high temperature, right? And we're trying to get rid of that through the cooling that's actually going down through the base, and the base is being held. The base is at 300 degrees Celsius, okay? So what ends up happening in this one then is the tip is going to be the hottest because it's going to be the furthest away from that cool temperature. Okay. So that means we need the temperature at X equals L. So we need a temperature at a given location, right? And that's where we go back to our equations here, and we look to see, you know, this is for a single blade. This is our temperature distribution equations, okay? So I think it told us assume adiabatic. Yeah, this tip may be assumed to be adiabatic. Okay, so then that means we're going to use this equation at X equals L. So X equals L, that's going to L minus L. So we're going to have 0. Hyperbolic cosine of 0 is 1. So you see right here, they've already kind of put in what thetas are. So this is theta. Let me make it further. At L over theta base. And they've already, already made that 1. Okay, and then, so we're looking for this temperature. We have all these temperatures. We need M times L. So M is that coefficient we solve for that describes in that fin equation. Okay, so all the parameters are kind of lumped together in there. We get our values, substituting them in, and m times L, we get 2.39. So plug that back in, and we get 1037 degrees Celsius, which is less than our 1050. Okay, so we're good there. Part B is the heat rate, right? So they ask for the heat through the fin. So that's where we can go back, and we see our fin heat rate. Okay, again, it's adiabatic tip, so we utilize this equation. So we need capital M. We already have M times L. All right, so capital M, we can see in this tables down here, those two parameters are given to us. So we're just looking for M. The other part I should say in this capital M, the theta of the base is not included in the square root. Okay, so that's when I see sometimes people thinking, students thinking that's in the square root. All right, and you can see that with how they're writing it down there. All right, so again, parameters, just rearrange. We get this, plug it in with our M times L and our hyperbolic tangent, and we get negative 508 watts. And it's negative because it's going into the base. Positive would be out of the base from this. Any questions? No? All right, then we'll move on. 3.114. Good amount of reading. An isothermal silicon chip of width W is 20 millimeters. On a side is soldered to a aluminum heatsink, where K is 180 watts per meters Kelvin of equivalent width. The heatsink has a base thickness, LB, of 3 millimeters, and an array of rectangular fins. Each of length LF is 15 millimeters. Airflow at T infinity is 20 degrees Celsius is maintained through the channels formed by the fins in a covered plate. And for a convection coefficient H 100 watts per meter squared Kelvin, a minimum fin spacing of 1.8 millimeters is dictated by limitations on the flow pressure drop. The solder joint has a thermal resistance of 2 times 10 to the negative 6 meters squared Kelvin per watt. Part A is consider limitations for which the array has n equals 11 fins, in which case values of the fin thickness is 0.182 millimeters. That's lowercase t, and the pitch, capital S, is 1.982 millimeters, are obtained from the requirement that W is equal to n minus 1 times S plus T, and S minus T is 1.8 millimeters. The maximum allowable chip temperature is TC equal to 85 degrees Celsius. What is the corresponding value of the chip power, QC? An adiabatic fin tip condition may be assumed. And airflow along the outer surface of the heatsink may be assumed to provide a convection coefficient equivalent to that associated with airflow through the channels. And then part B is, just more of an exploratory problem, part of the problem. All right, so in this part, we see problem. Most of what you had heard me read is a lot of the parameters, and then also there's a lot of, thicknesses, difference between the fins and the spacing of the fins. So trying for in these problems to describe that usually takes a little bit of time. So we have also given to us in the problem is this schematic you see on the left. Okay, so that's helpful with this one for sure, with all the things they're kind of telling us here, right? So we have a width 20. Also this way, even though it doesn't look like it in the problem. The temperature of this chip. Right here is 85. There's a contact resistance between it and the heatsink. Okay. We have thickness there of 3 millimeters from there to there, and then a length of 15. And then the others is the spacing and the number of fins. Right. So we end up with 11 fins. All right. So the tricky part in this one, you end up wanting the heat rate off of this, right? Maximum allowable temperature is 85, right? So we have 85 as our maximum. So that means we need the temperature to drop from there. Okay, so that's our highest temperature. So now heat's going to be going out in the lower temperature on the fins, right? So in this problem, there's a little bit more going on. We have this contact resistance. Okay, so what's easier in this problem is actually to do the thermal circuit. You see that on the right, which wasn't given, but this is from the solutions, is the thermal circuit, right? So we have this temperature of the chip, and then this is our contact resistance. Okay. Double C's. All right, contact resistance, there we go. And then we have one thing, it's tough to see, but right there, we have this thickness of 3 millimeters. And if you notice from here, the temperature of the base starts right there. It doesn't start here, it starts here. So this is the temperature of the base, right along here. So right along this surface. See that again right here. So in this problem that we're doing, we have some conduction that's going on from this location to this location. And that's this resistance, is the conduction from this location to this one. Okay, so that's this one that we have here. Okay, now the last we have is our fin array. And that takes us from the temperature of the base, which is would be right there, all the way to T infinity. So that fin array includes all the fins, the convection, the conduction that's going on it into one resistor there. Okay, so if we want now QC, we know T infinity, we know TC, so we can just take our thermal circuit across that of TC minus T infinity over total resistance. Okay, and so we know this temperature, we know this temperature, we need to get our resistance. That's our contact resistance. They gave us R double prime, so we're just converting it to R. We need the conduction through that little base thickness. So that's L over KA, so our cross-sectional area through the base. And we get our resistances for those two. So then last is the fin array, which is all the rest you see down below. So that has a little bit more of going through a bunch of equations. So we have that resistance for the total array, right? Fin array. So that's here, okay? So that's this equation. And inside of it, we have convection coefficient, which we have. So we have the overall efficiency of the array and the total area of the array. Okay? So first off, the overall efficiency is this equation you see here, which has a single fins efficiency. Again, has that total area, has the number of fins which was given, and then is the area of a fin. Okay. Well, we'll work our way through those. So the area of a single fin that cooling is occurring on is width LF times 2. So they're basically looking at the fin, and it's this area, and then on the other side, that area. Okay, so let me draw it over here. So so there's one side on the fin, and then they're doing the other side. Okay, and that's what the multiply it times 2 is. All right, so that's one single fin, and that's why you see it multiplied times the number of fins in the equation. And then the total area is, again, all the fins. So that's it right here. The total area is single fin times the number of fins. So that gives all the cooling area on the fins themselves. And then you have that exposed base. What's going on in between, right? And the simplest way of getting that is actually taking, and that's what you see here, is taking the whole base, which is this, the width times width, right? So width times width. All right, so that'll get us the whole base, and then subtracting off the part that the fins take on. So it's the thickness of the fins times the width, and then the number of fins. So that's like this surface. So we're just kind of taking that full base and then subtracting off the base area that the fins have. Okay. All right, so that means now we have base area. We can solve for our total area. We got an equation for that. We have total area, fin. So we need the single fin efficiency still. Okay, this is a straight fin. If we look at a single fin, it's a straight fin. So we go to our equations here, and this is what we have for a straight fin rectangular. So there's our fin efficiency for a single fin. And that's what you see them using right here. So then you just got to get this parameter M, and then the length. And that's what they're doing here. Okay, and we get 70.4%. Plug it in, get the overall efficiency, we get 71.9%. Plug it in to get the overall fin array as a resistance, we get 2. Now going all the way back up to here, we can solve for our heat that's dissipated through this fin array, and we get 31.8. Right, we see low resistance compared to the fin array, right? So fin array is 2, the others are order of magnitude 1 or 2 lower, right? 2 or 3 lower, I mean. So most of it's from the fin array. Okay, so we get 31.8 watts that we can have the power dissipating. So that could be the power of the CPU in this case. Now, if we didn't, let's say instead we just had the exposed area, no fins anymore, and we just had the base, and that's it, and basically no fin array, and just convection across it. In that case, we can only dissipate 2.6 watts. So we see an order of magnitude lower, right? 31 to 2, so 15 times lower, that we only can have our chip be at that power versus the other one. Otherwise, it's going to get too hot and short out, right, and burn up. Okay, so you see the impact that a fin array does. Any questions?
Yeah, Professor. Can you go up to the previous slide real quick? So my understanding was that the base area was the area of the base if the fins weren't there, right? So wouldn't that just be W squared?
No, so in this case, this is for the convection that's occurring on the base area.
Okay, okay,
So it'd be like this and this
got it.
and this. So you got to take the base area squared and then subtract off the area. And here in this one was, yeah, if it was all just base and that's it, right?
Okay.
In that instance.
All right. Okay, thank you.
Mm-hmm.
I do have one more question. I think it might be a little bit dumber, but so I don't have too much experience working with hyperbolic trig functions. So for calculating it, should we have it set to degrees or radians, or which is it?
Radians.
Okay.
Yeah. They might even have in the appendices those equations. I think they do. Yeah, I mean, yeah, in the appendix B1, if you wanted to interpolate, it has, as x changes from 0 to 10, they have the answer to the different hyperbolic functions. So you could always just interpolate your equation if you really wanted to, or you have it in your calculator, obviously. Any other questions?